Good day, everyone. My name is David Gigarnia. I'm with the Itasca Consulting Group in Minneapolis, and today we welcome you to our presentation or webinar on what's new and new features in PFC7. Today we have Sasha Amam and Matt Provence, who are the lead developers and product managers for PFC. So we'll have them give a presentation of what the new features are, and then afterwards there'll be should be some time for questions if you have any. In terms of questions, if you have a question, please just type it into the question dialog and go to webinar, and then we will answer the questions at the end of the presentation. If you're having any kind of technical difficulties or questions of that nature, please also submit them here, and we'll try to address that in real time. All right, so Sasha, if you'd like to continue.
Yes, thank you, Dave. So hi, everybody. Thank you for listening. So today we're going to cover the major new features that are in this version 7 of PFC. So we will talk about the items that are listed in this slide. So multithreaded FISH, particle inlets to generate particles at a specific flow rate during cycling, a set of new contacts models that are available in this version. Then we will talk about stress installation strategies, some feature enhancements, and then at the end we'll conclude by the availability of PFC on Linux. So diving into multithreaded FISH, so there are a few new concepts in FISH that allow for faster calculations. The first one is list splitting. So list splitting can be used to replace loop statements to perform action on the list of objects on a very clear and concise manner. So to do that, we introduced this new double colon operator, which is a split operator that can be given as a prefix to arguments of a functions. So for instance, this is a typical loop that we could do in earlier versions of PFC. Here it is to compute the maximum height of the balls in a 2D model. So typically what we would do is initialize a very low value, then loop over all the balls in the list of balls, take the maximum of the position of that ball and the temporary value. And if we want, we could add the radius also of the balls and then return the final value. This entire process can be narrowed down into just one statement. This just a code snippet where we do the same thing. We take the ball position, but this function operates over the entire list of balls that is split. And we can also add the radii of the balls and take the maximum of the values returned to get the maximum height. And so if the function is also multi-thread safe, it will actually be operated on all the threads available in the computer. So it will be much faster than the loop formulation. We can also add filtering to this. So if you have a list of booleans that is the same size of the list, you can actually filter the list to do something. So for instance, here we have just a line that will compute the average radius of the balls in the system. So we call the fish function ball radius on the entire list of balls that is split. We take the sum of those values and we divide by the number of balls in the system to have these average values. Line of code here, we will compute the average radius. So it's the same formulation as the first line, but this is operating only on the list of large balls in the system. And then we divide by the size of this list to compute the average radius of the balls only in this large group. There's another new feature in PFC7, which is the fish operator. So a fish operator is very similar to a fish function, but this is a new class of function that is designed to operate on multi-threaded environments. So just a simple example here. So instead of a fish function again, so this is a fish function that would actually loop over all the balls and assign a group to the balls if, in this case, if their radius is larger than a value. Now we can replace this statement by this fish function by a fish operator that will actually operate on an element of the list. It will do the same operation. So if the radius is larger than a value, then assign it a group large. And then we can call, so this new fish operator, it can be called using list splitting over the entire list of balls and assign the group. So it will perform the same operation in a much concise and much faster way. There are some restrictions when you use operators or list splitting, and so please see the documentation for further details. Those restrictions basically are linked to the fact that you need to operate on a multi-thread safe environment. And then the speed up that you can get by using operators will increase with the function complexity and the availability of the threads on your computer. Last example, so this is a function that is actually coming from the documentation. So this is a function that will loop over all the balls in the system to do some complex computation and add forces due to the presence of fluid in the system. So add a drag and a buoyancy force. So here what you see is that we loop over all the balls and we do some computation. And then for all the balls, we compute also the volume that is immersed under the fluid. And we sum those values in the end. This can be, with very small effort, this can be replaced by an operator. So the operator directly operates on one element of the list. So you don't have the loop anymore in this operator, but you do the same computation. And in the end, you return what is the volume emerged by that ball. So we add the forces, we do the same computation. And then we can then call this operator over the list of balls in a splitted way to perform in a multi-threaded, to perform the computation on multi-threads to get the same results. And for example, in this case, you can get a speed up of about 5 on my computer for the same operation. So now briefly, another new feature that is available in PFC7 is the particle inlets. So particle inlets are a way to generate particles or feed particles in the system during cycling. It builds upon the brick logic, meaning that you first create a brick. All the information about the position and rotation of the particles is stored in this brick. And then the inlet logic can use this information to create particles in the system at a specified flow rate. So this is something that could be done with a complex fish function before using balls, but was very involving if you wanted to use clumps or rigid blocks. Now this inlet logic is compatible with clumps and rigid blocks transparently. Additionally, the inlets can be positioned and are oriented in the system as desired, and they can also move, so translate or rotate at a to follow a specified trajectory during cycling. And also there are relaxation schemes that can be activated to prevent instabilities resulting from large overlaps when you insert particles in the model. So as the inlet is moving, you may end up with situations where there is overlap between the newly generated particles and the particles already in the model. So we have some relaxation schemes to prevent any instabilities of the model. This is a simple example of a conveyor. So this is using rigid blocks that are fed using this logic here in the entrance here, and then are moving into this system. Maybe I can show it once more. Okay, now jumping to the new contact models. So we have a set of new contact models in PFC7. We have a fish contact model, 2 adhesive models, and then we'll talk about the spring network contact model. The fish contact model. So basically, PFC is frequently used to introduce some custom physics in the model, and usually it requires implementing a C++ contact model. So implementing a contact model in C++, compiling it, and then linking it to the executable, which is maybe a difficult task to do. So in PFC7, we introduce a new simple contact model in FISH. So you can even implement a FISH function that will compute the force displacement law that you want and plug it in the PFC cycle sequence. The user can also define stiffnesses to plug in the automatic time step computation logic in PFC. And the contact state information is already fed and passed to the specified FISH function, so you don't have to worry about this. So this is a FISH way to implement a new contact law. It is approximately 4 times slower than a C++ contact model, but it is substantially more efficient than hacky FISH functions that would try to reproduce the same thing with previous FISH implementations. So this makes contact model development and debugging easier and simpler. And so we hope that this lowers the bar for people to start implementing new contact models, at least as a first step, and then after debugging and reflection, maybe move to implementing a C++, the same contact model in C++ for efficiency. So how does it work? So basically, you need to define this FISH operator that will take a pointer to the contact model and then to the contact and then the contact model, the contact state information. And then in this function, you can do the computation you want to update the force in the contact in this case. You could also update moments, but so this is a simple implementation of a linear model without viscous damping. And so when you do the computation, then you can set this new value of the force as a property of the contact model. Then, similar to other contact models in PFC, what you can do is add this contact model to the contact model assignment table. So by default, when a contact is created, this model, a FISH model, will be assigned. You can also catch this contact using a FISH callback event to initialize some values in the model, and also initialize which function. So this function linear model is the one that is that will be executed during the force displacement law sequence in the cycle sequence. So for each contact during the cycle sequence, this linear model function that we define will be executed, and the force in all the contacts will be updated. We have also 2 new built-in adhesive contact models that have been added to PFC7. One is the Johnson-Kedal-Roberts contact model, which is an extension of the Hertz contact model that accounts for attractive forces due to van der Waals effects. But it is also used in the literature to model materials where adhesion is caused by capillary or liquid bridge forces. We introduced a second contact model, which is the EEPA contact model, which stands for Hindenburg Elastoplastic Adhesive Contact Model, which is an extension of a linear hysteretic model. It is based on the work, on the PhD work by Morrissey, 2013. And so it allows for tensile forces to develop, as well as hysteretic nonlinear force displacement behavior in compression. And both of those models also incorporate viscous damping and rolling resistance mechanisms, similar to the rolling resistance linear model that was already present in PFC6. So just very briefly, this is a schematic view of the evolution of the normal force versus overlap for the JKR model on the left-hand side and the EEPA model on the right-hand side. So both models start at 0 overlap at contact with an attractive force. Then the GKR model has a nonlinear elastic formulation, similar to the Hertz model, but also is able to sustain tensile forces up to a tear-off distance where the contact will break. And the EEPA model has a hysteretic formulation So different stiffnesses in loading and unloading to account for energy dissipation by plasticity. And this is just an example, a demonstration of, so on the left-hand side, we have a model with the Earth's non-adhesive model, a regular non-adhesive model. And this is an animation using the EEPA contact model, so with some tensile forces to show the different, qualitatively, the different kind of behavior that one can achieve. So now we can move to the spring contact model, and maybe Matt, if you want to take over.
Sure. Thanks, Sasha. Hello, everybody. This is Matt Purvance. I'm also one of the developers for PFC. So I'll go through the rest of the slide set. One of the important additions to PFC 7 is the additional capability represented by this spring network paradigm. And basically what this allows you to do is create materials, this is for bonded materials, where there's no calibration required for elastic response. So you can match, for an isotropic material, match a target Young's modulus and Poisson's ratio without calibration, which is something that was been very difficult to do in PFC. And in addition to that, also reduces heterogeneity of elastic response in the model. So you can actually put the heterogeneity in yourself as the user versus it being dictated by the material microstructure. So here's a figure from Leandro Rasmussen, who brought this model to our attention. And basically what it does is it gives you a way via lattice theory to compute spring stiffnesses based on a zero Poisson ratio lattice. And this is what really removes the heterogeneity at the particle scale. Then there's an additional computation which relies on the stresses for the pieces in contact. So if they're rigid blocks or balls that are in contact or whatnot, based on the stresses of those pieces, there's a Poisson's correction through a fictitious force. And this allows you to match both the Young's modulus and the Poisson's ratio without calibration. Leandro has a paper where he's also extended this for anisotropic or materials that potentially plastoelastic materials. This sort of formulation could be extended to as well. And really, it's a big deal not to have to to calibrate to get a continuum response. This can be used for balls, rigid blocks, or clumps. It's independent of the type. It's not just, even though it's called the spring network model or rigid block spring network paradigm, it's not just really applicable to rigid blocks in this case. The failure response in this model is relatively exhaustive, so you might think of it as it's a little complicated. There's an example in the documentation that goes through the different characteristics of the failure response of the spring network model. Basically, it's like a parallel bonded material, so you calculate the maximum tensile stress at the bond periphery, so that includes bending for the tensile stress or tensile failure. It also supports arbitrary tensile softening as a function of continued elongation through a table. So you can assign a tensile strength as a function of elongation after it reaches the peak tensile strength, which can go down. It can actually go up as well if you wanted it. So it can be nonlinear stress strain response after a value. And the same thing, there's arbitrary slip weakening that can be supported as well. And that's what this plot on the right is showing, different scenarios with having rigid blocks on a surface that are sliding and then stopping to slide and then sliding once again, and showing the stress evolution. And so you can have slip weakening, linear slip weakening, or non-linear slip weakening It also supports healing. So if slip ceases, that it can heal, so the cohesive strength can go back up to be what it was in the original state. Other interesting things that this model can do, like the soft bond, it has bending and twisting frictional resistance. And we did include pore pressure. So you can set a pore pressure term as a stress that will then reduce the normal stress for failure computations. So it will give you, so the failure computations are then in effective stress space. This can be really useful if you have approximate, if you want to introduce an approximate constant pore pressure in the model. Moving on, so we'll talk about stress installation, which we spent a fair amount of time on for balls and rigid blocks. So as you may be aware, stress installation for ball assemblies, so this is for a packed bonded assembly, it's pretty challenging in 2D to get a relatively homogeneous stress state or to a target stress state. Why is that? Well, if you look at, this is just an example in 2D of a ball packing, if you zoom in and you plot on the right-hand side the contacts, there's a new plotting capability I should mention in PFC7, so it will plot contacts as joints, meaning that for ball-ball contacts, it will plot them as line segments or discs in 3D that have the correct area. So you get a microstructural representation of the contacts, different from plotting as cylinders or as discs in general, right? The same thing works for rigid blocks, where you'll get actually the faces, if the faces are in contact, you'll actually get the shape of those faces with the appropriate area, right? So I'm plotting the joints over here, what we call joints. So this is actually a microstructural representation of this bonded material. These are the contact areas. And you can see on the right, they're kind of all over the place. This makes it pretty challenging to actually set the stress state. So you can get an idea, if you had a uniform stiffness, you would get a lot of heterogeneity and elastic response too. But for stress response, it's really difficult to get this to a target stress state. If instead we think about this problem differently, what has a microstructure similar to a ball packing, where we can actually, instead of relying on this relatively simple way of setting the areas of the contacts, we can rely on a consistent formulation between the surface area enclosing a volume and the volume itself that's enclosed. Then we could potentially set the stress in a much more consistent and homogeneous way. So what we actually do is we compute a weighted Voronoi tessellation, so meaning that as you can see, there's a weighting for the ball, for the Voronoi cells over here. So you have some small cells that correspond to some small balls. And you have larger cells corresponding to larger balls. So I think it's actually called a Laguerre tessellation. And then we can update the ball volumes and positions to be consistent with these Voronoi cells. So that means that the volume or the area in 2D of the ball is consistent with the Voronoi cell. So the contacts have the area that's consistent with the enclosed volume, and the balls have the volume that's consistent with the Voronoi cell. So so this would be like a zero porosity initial packing. And this level of consistency between the enclosed volume and the surface area allows you to specify the stress in a much more homogeneous way. So this is using the ball tractions command. So basically all the contacts are created at the Voronoi faces from the previous plot, and we assign the correct face areas to the contact areas. And subsequently, we can compute tractions, which are really the surface forces or contact forces. A traction is a surface force, right? And that's what we have. Our a bunch of objects in contact. We have forces at the surfaces, rigid objects in contact. So what the ball tractions command will do is compute the tractions consistent with these areas. And so you go from a kind of microstructural joint plot like this on the left to something like this on the right. And subsequently, if I installed a stress state, which here was, I think, is uniform, 1e to the 6, in the x direction, and in the y direction, 1e to the 5, you can see that it's not perfect stress state, but it's quite homogeneous. This is very difficult to achieve in general for packings of granular materials, bonded packings of granular materials. You can also see here that there is a stress deviation, and this can be expected at the boundaries. So oftentimes what the best practice is to actually create a specimen, install the stress, and then trim it to a smaller container size. Because also, as you might see in this plot, the balls actually end up being aligned with the boundary as well, which happens. This assembly was just generated first by generating a bunch of balls, blowing up their radii, allowing them to equilibrate, and then calling the ball tractions command. But near the boundaries, and this can happen with meshing in general, you tend to get balls aligned or rigid blocks aligned near boundaries. So it's generally a very good idea to install these stresses on an assembly and then trim it to a smaller size so we can get rid of these boundary effects. But nonetheless, these two stress states are quite homogeneous, right? This can be applied as well, and I mentioned it's the ball tractions command. There's an equivalent rigid block tractions command, and both those commands were modeled on the zone initialized stresses command from PFC3D. They allow you to specify a constant stress state, so you can have a totally isotropic stress state. You can have gravitational stresses, so a depth-dependent stress state. You can also have the horizontals be proportional to the depth-dependent stress state. It also supports variable density layers, so that you could have a stress state which varies as a function of depth, dependent on the overburden, right? So you can have increasing density, and the stress state will be set according to the way that density varies as a function of depth. You can install anisotropic stresses and just a general overburden term as well. So you can say that this is at some depth and install stresses to there. So this is just an example using rigid blocks where one command has allowed you to specify this is the horizontal stress and the vertical stress, and the coloring is at the same scale. You can, with one command, relatively easily, this is after cycling, so there was some slip on some structures in this region, but after, you can, with one command, just very simply set in situ stresses, and that's a big deal for PFC. That's a big modification for these types of bonded assemblies. Moving on to some more feature enhancements. So I'll talk about the generalized clumping logic that's in PFC7, enhancements to rigid blocks in general, and our leakage to the PFC3D structural elements. So the clump logic has been generalized. Before clumps, you could just have pebbles, which were spherical particles. Now, the clumps can be composed of balls or clump pebbles or rigid blocks. It really only makes sense to say balls and rigid blocks, I think, right? And you can make then composite clump templates. And how you would really go about this is to generate the balls or the rigid blocks that are going to make up your clump template. You can create a clump template from those pieces, and then you can replicate them just like you replicate clumps right now. So you could have 5 balls and a rigid block if you wanted. There are always obviously performance benefits to having pebbles be balls. So but there are benefits to having rigid blocks be pebbles as well, which I'll show an example of. They can be clumped while cycling, which makes it really nice. So you can and also retain the exterior contacts on the outside of the clump. So you could just say, take this region of space, which doesn't have much action, make it rigid, boom, and you lose all the internal contacts, so you speed up the computation. It becomes one rigid thing, but all the contacts on the outside remain, right? So without much disturbance, you can do that, which can be nice for models in general. You can also later free these pebbles. So you can be cycling and decide that you didn't actually, that it's broken, or that those should no longer be clumped together as a rigid thing. So you can use breakage simulations. And as a simple example, here is a dolos, which put in the ocean to prevent erosion at coastlines. And I made a clump template out of that, where these are all rigid blocks. So there are 5 different rigid blocks, and the simulation showed them falling. And then what it's showing on the right is they were all the dolos on the right-hand side of the simulation were broken or freed. So all the individual rigid blocks were allowed to be their own entities. And let's see if it goes back. Yeah. It will play. But the basic idea is, that's okay. The computational performance of this rigid block-based clump is about equivalent to a 31 pebble clump composed of spherical particles, right? The contact resolution between rigid blocks is more expensive than between spheres, which is basically free or very cheap. But on the other hand, there aren't these bumpy surfaces that you would use with a regular clump composed of spherical pebbles. And this can have a pretty large impact on what you see in the final outcome. So if I actually look at taking in the top left figure, this is using rigid blocks as the clumps. So 5 rigid blocks making up one clump, one dolos, and allow those to settle. This is the result with with 31 pebble clumps. And so this is about the same computational speed, but you can see quite a difference in the amount of packing. This is just being settled under gravity. There's no shaking or any other input to the model. What you can see is that there's substantially more volume on the left than on the right, these 2 top figures. Why is that? Well, it's because these rigid block clump templates, or the rigid block individual pieces, they're actually larger volume for sure, but they also don't suffer from having this bumpy surface. I mean, larger in the sense that it fills the actual target volume more appropriately. And in fact, so what you can do with the clump logic in general is increase the number of spherical pebbles inside the clumps to get an idea of how many pebbles are necessary to give us kind of the same sort of volumetric packing. And as you increase the number of pebbles, what you end up doing is you increase the number of contacts overall, because there can be a contact between each spherical pebble of one clump and each spherical pebble of another clump. This drastically reduces the performance, right? So when we go from a 31 pebble clump to a 47 pebble clump, which this is about 2 times slower than the rigid block model, you can still see that the volume is lower, just due to gravity settling. And even when you go to a 91 pebble clump, which is about 10 times slower, you can see that there's, so the kind of the middle of this section relative to here, the volume's still lower. And so basically what it allows you to do is say with a higher, in a sense, with a higher fidelity, you can model concave particles using this generalized clump logic. Moving on to kind of generic rigid block enhancements. So the rigid blocks we've done quite a bit of work on rigid blocks, with the goal being able to both do granular flow simulations, but also to do bonded block style simulations. So simulations which would be very similar to what you do with 3-deck, except using the rigid blocks instead of using deformable blocks in 3-deck. So we've enhanced rigid blocks. You can assign facet groups. So on the facets of your rigid block. This really allows you for simple boundary condition application and also easy contact assignment. So you can, for instance, cut a rigid block, assign a face group to both sides of the rigid block that's been cut. So you're cut it into two, so you have two faces, and now you can capture that as having.
Oops, I'm not hearing Matt again. Okay. Yeah, you're back.
Sorry, I apologize. My headset died. I don't know exactly where I was, but if this is adequate, then I will continue this way. So what I think I was saying is that, yes, you can apply facet groups. And this allows you to do some nice things with cutting of rigid blocks, if I said this or not, but basically you can cut with a DFN. You can assign face groups to the cut surfaces, and then you can capture those to put different contact properties or contact models in those cuts. Also, you can cut rigid blocks while cycling and retain the contacts. This is kind of a big deal. So this can simulate grain breakage with some sort of fish criteria, and I'll show an example of that in a moment. There have been performance enhancements for unbonded contact resolution between rigid blocks, so it goes faster than in PFC6 by about, depending on the model geometry, 10 to 20%, so not huge, but still enhancement. As we mentioned, there's a stress initialization strategy, and we do have simple meshing that's been augmented somewhat with this new version, especially with some densification. So densification is a strategy to actually do recursive cuts of rigid blocks through their centroids. And what it really allows you to do is to make a higher resolution set of rigid blocks in different areas of your model that work reasonably well. So all of these things kind of come together to be able to create some models which are very compelling in our opinion, very similar to what happens in 3-deck, what you can do in 3-deck. So in this case, I'm showing a comparison between a 3-deck model on the left using deformable blocks. This is a staged excavation of a complex tunnel geometry that has complex boundary conditions, a lot of cutting with joint sets, DFN cut into it on the left, and this is the same on the right, the same thing using rigid blocks in PFC, going through the same process with joint sets, with cutting, with the boundary conditions. It's stress installation. So what's really nice about this is that you can use those facet groups to assign those boundary conditions, to fix the contact properties, because there are different properties in different parts of the DFN, right? So you can easily manage that now. There was no elastic calibration because this is using the spring network model. So you just set a Young's modulus and Poisson ratio, just like you would in the 3-deck model. As I mentioned, the DFN logic, which is used for cutting, that has a joint set capability, just like in 3-deck, how there's a joint set capability in 3-deck. So really, you can make these sorts of models now in PFC. The big benefit is that it goes a lot faster than in 3-deck. The computational performance is quite a bit faster. So in this case, this is 4 to 10 times faster than the equivalent 3-deck model on the same piece of hardware. And that's a big deal. There is a downside, though, that these are rigid, of course. They're deformable blocks on the left and rigid on the right. But our contention is that you can get a very, very similar response using the spring network model. So all the tools have really been put in place to do these sorts of simulations, and that was a big push for getting PFC7 out. And as an example of, so that example was just basically like a 3-deck model running in PFC. here's an example of something you can't really do in 3Dec. This is a 2D example, but to highlight that grain breakage that we can, as a new feature in PFC7. So in this case, there's a circular hole in 2D. It's initially in an isotropic stress state, and the blocks are based on Voronoi cells, right? So it's a Voronoi cell specimen. And we're going to squeeze it laterally to twice the stress, the initial stress. So the lateral stress is twice the vertical stress. And there's a breakage in criteria in fish based on the minimum principal stresses, whether they exceed a certain value. And then if that happens, those blocks are cut, right? In this case, what we're showing on the right is the original geometry of those Voronoi shaped rigid blocks. And in the bottom, these are cut rigid blocks that are just responding to the change in stress, right? So they're just using this minimum principal stress criteria for breakage. And you can clearly see a notch forming in this broken material above the circular hole, right? And so these sorts of simulations could be done for bonded materials like this, or also for granular materials. You could crush blocks or and allow them to break if you have some sort of a breakage criteria via cutting. So we think that this is a really useful application of a new feature in PFC7. And finally, for the enhancements, we have structural element support. So all the FLAC3D structural elements can be used with balls or clumps or rigid blocks. And that includes liners, shells, geogrids, and all the 1D structural elements. So beams, cables, hybrid bolts, and piles. So the hybrid bolt implementation is the FLAC3D hybrid bolt implementation. And this has been ported to PFC relatively recently. Here's an example on the right, similar to like a 3Dec example that shows a tunnel, staged excavation of a tunnel where hybrid bolts are being deployed as the front of the tunnel advances into the model. And you're getting some displacement in the, or force that is being taken up by those hybrid bolts, right? Just as an example. We're getting close to the end, so I'll briefly mention the Linux version and then conclusions. So we've spent a fair amount of time getting the codes version 7 and the newer codes, the next releases, to compile in Linux as well as in Windows. So if you go to our website, you can easily see, if you go to the updates page for PFC, you can see there's a link for a Linux version. I put the total address here. But what is the Linux version? Well, it's a fully functional GUI and console version. And when you install it, it actually installs PFC7, 3Dec 7, and FLAC3D 7, a version of those in Linux, right? Save files are compatible between the different operating systems. So you can save a file in Windows and open it in Linux or vice versa without any problem. Data files are compatible as well. But one thing to be aware of is that in the Linux file system, file names are case sensitive, but not in the Windows file system. So if you're calling a file with a capital F in the beginning, and it actually is a lowercase f, how it's saved on disk, then that won't work in Linux, whereas it will work on Windows. So that's something to think about. This was created using Ubuntu 20.04 LTS, or the long-term supported version of Ubuntu. And it will natively, the deb package that you can download from the website will natively install and run on that. If you would like to run it on a different flavor of Linux, it's very easy to create a Singularity container from Ubuntu 20.04 that can run anywhere. CentOS, we've tested on CentOS and Red Hat and others, and there's not really a performance hit, which is very nice. This does require a web license, so you can't use a regular dongle. You can use this on Amazon Web Services, AWS, which is one of the main motivations for this, getting us prepared for cluster or for MPI down the road. If you want to spawn a cluster, it's much cheaper and easier using Linux on Amazon Web Services or in a general compute center than it is to use Windows, right? So that's where we're moving with this. It really has similar computational performance to Windows. I will mention that the C++ context models are easier to compile because you have to do much less installation than you have to do on Windows. It doesn't require Visual Studio. Qt comes with the installation, so there are some easier parts there. And it has all the documentation, all the examples and verifications, and this is run through our build and test system, just like the Windows version is. So it's running all the same tests that we run to make sure it operates correctly. If you're interested in this, I think it's great, and I've been using Linux a lot, and for me, it's been a really great transition. So anyway, in conclusion, what we'll say is that we do think these new features open a whole new realm of possibilities with bonded block modeling and doing rocks mechanics type simulations similar to 3DEC, which are much more efficient to 3DEC. Also with the generalized clumping and the cutting of rigid blocks during cycling. We really think that this can be a boon for granular flows, for manufacturing, and for soil mechanics applications, also with the new adhesive models, right? Multi-threaded fish really is a game changer if you're doing a lot of fish during cycling. It can really speed up performance substantially. As I mentioned, the fragmentation abilities there and the spring network approach, we think those are really promising. Also, we didn't put in the conclusions, but the inlet logic can be really helpful for especially manufacturing and granular type simulations, right? What we're working on now are making more examples, better documentation, and please, we're always open for your comments and suggestions in that light. We're looking for more features to continually make it easier to use PFC, and we think we've done that with the rigid blocks to a large degree. Your suggestions are always welcome, and we're moving towards doing MPI or cluster computation, so that was part of the Linux port. And we anticipate that down the road we'll be able to fire up PFC and run it on many different, in a massively parallel environment, to be able to do much larger simulations or faster simulation. So with that, I will say that I'm done presenting, and thank you for your attention.
Great. Thank you very much, Matt and Sasha. So we do have a few questions. I'll just bring up that. And we'll go through these, and hopefully Matt or Sasha, one of you, can pop in with an answer. So the first question is, can you please elaborate more on the reason why calibration is not needed for the spring network model?
Sure. And maybe I didn't quite say it, calibration correctly. Calibration is not needed for the elastic response. So for the target Young's modulus and Poisson ratio, calibration is required for strength, right? And for a failure response, as it is in 3DEC and in other models. So I maybe didn't say that or highlight that quite correctly. Why is calibration for elastic properties not required? Really, it's because of the use of lattice theory to compute the stiffnesses at the contacts. That's something that we don't do in the other contact models, at least effectively. And also this force correction for the Poisson's effect, which is based on continuum theory. So the spring network model for the elastic response, interestingly, is really this kind of hybrid discrete continuum model. It's doing a discrete force displacement law where relative displacements are causing forces, but then it's saying, well, hey, what's the stress on the particles that are in contact? And if I have that stress state, what additional forces would I need to add to get me to the correct Poisson's ratio based on continuum theory, right? And this really gives you a very nice continuum-like elastic response. And as I said, also removes the grain scale heterogeneity and elastic response. So I think these are really powerful tools for bonded block or bonded ball SRM style models. I will say though, one additional thing, and then I'll stop talking, is that also if you have a ball assembly, you really want to use the ball tractions command first, so that you, even if you're not installing any stress, so that you get the volume and the surface areas consistent. Then you can use the spring network model as well, so that you don't have to calibrate those elastic properties for a bonded material. So again, this is only for bonded materials, not for granular flows or unbonded materials. That's all.
Great, thank you. Okay, next question. Does the stress installation via Voronoi tessellation also develop in PFC3D?
Yes,
Yes.
both in 2D and 3D.
Okay, great. Homogenizing the stress state seems appealing because it makes the overall stress field of the model more uniform. But how does that kind of homogeneous stress field impact the model behavior? In DEM, macro behavior emerges from micro behaviors. Those micro behaviors are sometimes driven by heterogeneity. How would a modeler know if they're making some desirable model behavior by making the stresses too uniform?
Sure, I can speak to that. Yes, I agree that heterogeneity in bonded materials often can lead to stress. It leads to stress heterogeneity. So heterogeneity in elastic response or in packing leads to stress heterogeneity. And in a lot of cases for discrete systems, we think this is what causes it to be a discrete system. Well, the thing is that the power of this model, in my opinion, and this is highlighted in Leandro's work as well, is that if you pack up balls, you put a stress state in, the stress state really ends up being responsive to the packing. And so what you need to change then in order to change the stress state or the heterogeneity and the scale of heterogeneity is the packing to start with, right? This is complicated. This is a complicated thing to do. The flip side, if you can remove that heterogeneity of elastic response at the grain scale, and you have something that's much more continuum-like, much more 3-deck-like, you might argue, then you can actually go back and control and reintroduce the heterogeneity by varying, for instance, the strength at the grain scale. By varying, you could slightly modify the elastic parameters, right, to introduce the stress heterogeneity. You can control this in a much more user-friendly way versus just trying to control the packing, which I think is very hard. In my experience, it's very difficult to control the packing because you're talking not just about porosity, but geometry, size distribution. You're talking about a lot of parameters there, whereas you can just go right. This has, in my opinion, fewer parameters. You're trading things off, but you can introduce it yourself. So I think that that's the real strength. And it is up to you to decide what kind of heterogeneity is important for your physical system. But doesn't just emerge from the packing in this case. So there are trade-offs.
Okay. Can the rigid block surface be concave?
No, a rigid block surface for an individual rigid block can't be concave.
Yeah, so this is the way we have this generalized clumping logic. So you can clump multiple rigid blocks to then get a concave surface.
Okay. If one already has the Windows version with a license, should one additionally purchase the Unix version?
So at the moment, the way that it works is that, as we mentioned, you can only use a web license. So if you have a dongle, a USB dongle, that won't work for the Linux version. You could convert your dongle to a web license. That would allow you to run either the Linux version or the Windows version from that web license, right? So at the moment, the way that we have it structured for PFC7 is that you don't have to purchase an additional version. Now, if you want to run things on Windows and you want to run things on Linux simultaneously, then you may have to purchase additional licenses, right? But at the moment, if you have a web license, it could run either the Windows version or the Linux version.
And just to add in, for those who may be a little familiar with our recently new web licenses, we have actually opened them up, and you may now run 2 instances on the same computer with PFC7 and some of our other software. So there was previously a limitation of 1 instance per PC, and we've removed that. And so there's a lower barrier now. If you're interested in getting a web license, you can convert a USB license to a web license if this is something that you're interested in. Next question. If a very large compressive stress at a point changes to a very large tensile stress, what is your interpretation of the change in state of matter?
Oh, I'm sorry, I didn't get the question.
Let me...
If a very large compressive stress.
So, yeah, if my understanding is correct, what you mean is that if you go from a very large compressive stress, so you're squeezing something really hard, and then you turn around and start pulling it apart, what's our interpretation of the material, or what's happening to the material at that point? Pull it apart very hard. And I think this is one of the beauties of PFC. So the individual particles are rigid, right? Meaning that if you had 2 particles together, but the action that's producing a force between them is happening at a contact, right? So if you're squeezing them together, there's a repulsive force that's trying to keep them apart. If you turn, and they're rigid by default, right? So they're just going to stay, they're not going to deform themselves, but all that load is going to be carried in that contact. Squeeze it, squeeze it, squeeze it. Then if you turn around and start pulling it apart, those balls will still have the same size, those particles would still have the same size, they're rigid, they're non-deformable, but then it'll go from a repulsive force between those 2 particles to a tensile force, right? So in general, for DEM with rigid particles, you might not think that's super realistic, because if you squeeze it too hard together, it could potentially crush. Or if you pull it apart too much, it might fracture, not just break at the contact, but it might fracture. And this is what we've tried to do, is give you as the modeler the ability to, with rigid blocks especially, or with clumps, to actually simulate this breakage process yourself, not just at the contacts, but also by cutting or breaking the object. So I think the real thing is what is your interpretation as a modeler of what happens in these scenarios, and what can you do with the model to try to get you to what you think is the real physics or the real response in material. So that's my answer, at least.
Okay. On the next question, thanks for the presentation. Is it possible to create a porous medium with non-overlapped connected balls with PFC abilities such as tessellation, and for where dimensions of the medium, radius, and number of the containing balls for creating the model are specified?
If I understand correctly, you mean pack an assembly of balls and then use this information, so the position and the size of the balls, to actually inform the tessellation. And yes, this is possible. Basically, there is our block construct from balls command that will let you do exactly that. And so you can construct a Voronoi tessellation based on the original position of the balls and also their sizes to get a Laguerre tessellation, as Matt mentioned before.
Yeah, and I should say, though, those tessellations will be space filling. so they will not have porosity in them. If you want to add porosity, then that's something that would have to be done with fish, but could be managed through the cutting logic as well.
Next question. Thank you for the presentation. I think in page, I don't know if it's a typo, 32 to 23, maybe it's 22 to 23. Example, when the breakage happens, is it possible to measure the size of the fragmented particles?
Yes, you could compute the volume of those particles after breakage, before and after breakage. This is something that is actually automatically computed by PFC. So you can have a distribution of those sizes.
Great. And that's actually pretty easy to plot as well, is it not?
Yes, you also have plotting access to this value.
All right, great talk. How would the applied forces on broken rigid blocks be immediately after failure?
Sure, I can answer that. So if you had two rigid blocks that are cut or broken based on your criteria, then what happens is, so you're taking one block that had contacts on its exterior, you're splitting it into two based on some criteria and a cut. So what the logic tries to do is go back with those pre-existing contacts with the outside world, right? So meaning all the adjacent rigid blocks or balls or walls or whatever, to install those at equivalent positions on those cut rigid blocks, right? So the goal is to not lose those forces that have happened. And then what, in the interior where you cut it, obviously there was no contact there before, it was rigid. And so a contact is created at the point of cutting. And in the next cycle, it will start accumulating forces. So initially it has no stress as if you cut it just directly during cycling. If you could, of course, because you could cut it, you can apply those face groups to the cut. So you could say this is a cut face against a cut face. A contact's created, you could catch that contact creation event, and then if you so desired, you could go and specify the forces explicitly for that newly created contact between the two cut blocks to be what you thought was appropriate. Because there's a question, it depends on the failure mechanism. If it breaks in tension, right, you're pulling this apart, you have a failure criteria that's based on tension, then there probably shouldn't be any force there at all, right? Because the thing is just broken directly in tension. Now, if it was breaking because of a shear, that could be a totally different scenario. And as a modeler, that comes, what you might set those forces to be comes down to what you think they should be. But by default, there's nothing between the cut pieces, but the exterior contact forces remain.
And Matt, I think the question was also about the applied forces. So let's say you apply boundary conditions to a face of a block, and then that block is cut into
Oh yeah, I was thinking of it in terms of contact forces. Yes, if that was the question, if it's near the boundary, first off, I would say that you probably want to see most of this failure internal to the model, where you're not applying boundary conditions directly. But that's actually a good question. I think that for the apply conditions on the rigid blocks, those would be retained. Those are copied. It tries to copy all the information from the underlying block to the new block. So if there were face apply conditions, those would be copied. So.
Okay. Is CFD plus PFC supported in version 7? So computational fluid dynamics.
So this is the same. There's no built-in CFD solver in PFC, so neither in PFC 6 nor in PFC 7. What we support is the ability to actually interface with with a third-party solver, and there are a few examples in the documentation to couple with a Python solver, and there is in PFC6 something to couple with a OpenFOAM solver, but I believe we would need to update. It would require some work to update to the latest version of OpenFOAM and PFC7 to be able to operate. But so we don't provide actually a CFD solver directly built in a PFC.
Yes, and I didn't mention it, but we should have mentioned it, that the Python version, which was 2.6, so we ship PFC with a scientific Python distribution, a curated scientific Python distribution. That's updated to, or 2.79, I guess is what it is in PFC6, is updated to 3.6 in version 7, just like FLAC3D7. And the equivalent Python packages are shipped with Linux as in Windows. Yeah, so we have the same Linux Python environment and the same sort of coupling as you do in Windows. I should have mentioned that.
Okay. Does thermal option, heat conduction, thermal expansion, thermal stress, work also for bonded block models?
Yes, it does, just as with balls.
Is it possible to apply all types of contact models on rigid blocks as well as balls and clumps?
Yes, all the contact models can be, you have the control or the capability to have all of the contact models happen in any circumstance.
Great. Can the cluster of balls become clumps during cycling?
Sorry, could you repeat that one again?
Yeah.
A cluster of balls can be clumped. Yeah.
Okay.
Yes, as Matt mentioned, you can at any time during the simulation you can decide to create a clump from multiple objects, so from multiple balls or rigid blocks.
Okay. How can diaperic movement be modeled?
I'm sorry, I didn't.
Yeah, diaperic, diapiric, diaperic. I believe I'm pronouncing that wrong.
I'm not 100% sure. You could please send us an email with a specific question and a few more details. And you can get both of our email addresses from the web easily from our website.
Yeah, so on our website, if you go to www.itascacg.com and go to the About menu, you'll see our staff listing there, and you'll see both of Sasha and Matt's emails.
And there's actually a centralized email address, which is the PFC support at itascacg.com that you can use to send emails, and this will be treated in a more efficient fashion than if you send it to individuals.
Okay, great. Is it so that once bonds are broken, they can be rebonded if shear slip stops? If so, does this mechanism also apply to smooth joint contact models?
Yeah, so this is only been implemented in the spring network model, healing after slip, not in the smooth joint contact model at the current time. But this is, again, one of the reasons that we put in this fish contact model, especially anticipating that there really aren't that many smooth joint contacts in a model, for instance. There aren't that many, most of it's bonded. And so you could really relatively easily implement your own smooth joint contact model with fish and allow for healing. And we just think that it really lowers the barrier. I know you would like us just to implement it, but it really lowers the barrier to you being able to put in the physics that we don't have into your model.
So we have a few more questions left. If I remember correctly, the DAM4 network model has been implemented in PFC7. Is this correct? So it was a DEM/4 network model.
People have implemented that for research activities, but it's not in the documentation of PFC. Yeah. This is not something that we ship with the software.
Is it something that's in the UDM library?
No, not even.
Okay. Okay. And then I think we've answered that last question already. So that concludes the questions that we have so far. Thank you very much, everyone, for joining us today. We hope you found it interesting and are curious in learning more about PFC7. Thanks to Matt and Sasha for presenting today. And also just to let you all know, the presentation video will be available online a little later this week. So we'll be sending you an email with a link to that. As well, we're going to be offering a free 2-week trial of PFC7 to people who have registered for the webinar today. And so that's something that we will also send you an email about if it's something you're interested in. So this will be a fully functional version, unlike the demos, which have model size restrictions. And again, it'll be valid for a couple of weeks. And we will send you more information about that if you're interested. So again, thank you everybody for joining us today, and hope you have a good rest of your day. Take care.
Thank you very much.
Yes, thank you.